Okay, this week we study matrix and the differential equations. Matrix is a list of numbers displayed within parentheses. These numbers are called entries, and each entry is coming from the field that is called sometimes a real number, sometimes complex number. In general, we consider the case of complex number. Aij stands for the ij element of the matrix. Sometimes we call as Aij as ij element or ij entry. I stands for the row. This is the first row, second row, and mth row. And this is the first column, second column, and nth column. Here we write m by n. That stands for, the m stands for the number of rows, n stands for the number of columns. We call this I and j, that stands for the column or row, as a index. The I and j are indices. With a matrix, we can compactly rewrite the linear equations, such as suppose that we have two linear equations, 2x plus y equals 1, x minus y equals 2. And by collecting the coefficients of 2, 1, 1, minus 1, we list these coefficients in this form as a matrix. And these two variables, x and y, are collected as a column vector. And this matrix and column vector product is actually this first row multiplied by this column is the left-hand side of the first equation. And second row multiplied by this column stands for the left side of the second equation. Let us consider the matrix operations. First of all, we consider the addition of the two matrices. Addition or any other operation of matrices can be defined by the relationship between the all elements. The ij elements are defined by something. For example, if I add a and b, then ij element, the ith row and jth column, ij element of this sum matrix is actually the sum of ij element of A and ij element of B. This is true for the whole entries. Next, we consider scalar multiplication. Scalar multiplication is a multiplication of a scalar C to a matrix A. This number C is multiplied to every element of the matrix A. So the ij element of CA will be the ij element of A multiplied by C. Next, we consider the transpose. Transpose, that is denoted by AT, the superscript T, is the matrix that can be obtained by exchanging the row and column. For example, we have matrix 2 by 2 matrix 1, 2, 3, 4. This is the first row, second row. If I put this T as superscript, then we need to calculate the transpose of this matrix, and transpose is obtained by flipping the up and down side with respect to the diagonal element. This is a diagonal element. 1, 1, 2, 2, 3, 3, 4, 4. These are called the diagonal elements. So if I flip this upside down, then I obtain the first row, 1, 2, is replaced with the first column 1, 2. The second row 3, 4 is to be replaced with the second column 3, 4. Transpose can also be applied to arbitrary matrix, n by n matrix. For example, we have 3 rows and 2 columns. And this 1, 2 is the first row, will be replaced with 1, 2 as the first column. 3, 4, the second row, will be replaced with the second column, 3, 4. 5, 6, the third row of the original matrix, is transposed to obtain the 5, 6 as third column. So after applying the transpose operation, we have column, row index and column index will be exchanged. Next, we consider Hermitian Conjugate. Hermitian Conjugate is a matrix that can be obtained by, that is denoted by a dagger. A dagger means A dagger ij is the complex conjugate of AJI. That means AJI means if I begin with the A as A, B, C, D, first I take the transpose, that is A, B. This row will be replaced with this column, A, B, and C, D. This is transpose. After taking the transpose, we take the complex conjugate. Complex conjugate means take the complex conjugate of every element, a C star, B star, and D star. This operation can also be obtained by taking the complex conjugate first. And then take the transpose. Okay. For example, I have a sigma matrix, Pauli sigma matrix, sigma 2. If I take the transpose, then if I take the complex conjugate, so this is sigma 2 dagger. We find that sigma 2 dagger and sigma 2, they are the same. If it is a case, we say this is a Hermitian matrix. Hermitian is a dagger becomes itself. Next, we consider multiplication of matrices. If I have 2 matrices, for example, I have a single row matrix and single column matrix. Element 1, 2, 3, 4, A1, A2, A3, AN, and B1, Bn. That means if I have a single row, I have n columns. And this column matrix has rows, and this number of rows must match with the number of columns of the left matrix. When these two numbers matches, then we can multiply two matrices. So matrix A multiplied by B, the ij element of this will be, this is a row index, and I sum over K, and this K is summed over from 1 to n, the number of rows of the left matrix, the number of columns of matrix, and the number of rows of matrix B. Here, I should put this K runs from 1 to n. However, we will remove this one in case we have repeated indices. This is called Einstein's notation. Summation convention. Next, we consider the identity matrix. Identity matrix is matrix whose diagonal elements are all 1, and off-diagonal elements are all 0. So, as I just told you, these elements, AII equals 1, AIJ equals 0 if I is not equal to j. So, special notation is used to identify the ij element of identity. We use Kronecker delta. Okay. Next, we consider inverse. Inverse is a matrix such that the product, let us consider matrix A, and if I multiply some matrix B to the right and to the left, in either case, I always obtain the product as identity matrix. Then we say B is the inverse of matrix A. Next, we consider the trace of a matrix. A trace of a matrix is a sum of all diagonal elements. Trace I have matrix A, for example, sigma 2, 0, minus I, 0. Diagonal elements are these and these. So, trace of sigma 2 is 0 plus 0 is 0. If the trace is vanishing, we say traceless. Another example of a traceless matrix is a Pauli sigma matrix, sigma 3. 1, minus 1. This case, sum of diagonal elements will be 1 minus 1 equals 0. Next, we consider the symmetric matrix. Symmetric matrix is, suppose we have matrix A, B, C, D. If I take the transpose, diagonal elements are invariant, and this will be flipped in the C, D. Okay, then I would say A is a symmetric if the matrix is the same as the transpose of that matrix. That means B, C, they are the same. For example, 1, 2, 3. What is the element of this? This element should be, if this is a symmetric matrix, and this one should be 3. Okay? So, asymmetric matrix has 2 diagonal elements, they are free, and off-diagonal elements, they are correlated. And only in this 2 by 2 case, we have only 3 independent variables. Next, we consider the orthogonal matrix. An orthogonal matrix is a matrix such that its transpose is the same as inverse. That means, for example, I have rotation matrix R theta, cosine theta, sine theta, minus sine theta, and cosine theta. Its inverse is obtained by just replacing this angle theta with a minus theta. Then, because the sine is an odd function, we have sine theta minus sine theta. And cosine theta is an even function, so cosine theta, cosine theta. This one is actually the R inverse, R theta's inverse. However, it can be simply obtained by taking the transpose. If I take the transpose, these two elements are flipped. So just the transpose of this original rotation matrix is the same as inverse of the original matrix. Therefore, we say the R transpose is R inverse. That is, R is an orthogonal matrix. Hermitian matrix, I already told you about the Hermitian matrix. It is Hermitian conjugate, that is transpose complex conjugate, or complex conjugate transpose. This is the same as the original matrix, then we say this Hermitian matrix. Another one we need to know is unitary matrix. Unitary matrix is, if I take the Hermitian conjugate, then it is just inverse. Then we will say this is a unitary matrix. In the operation of matrices, we have a number of indices. In case we have repeated indices, for example, product of AB, ij element will be expressed as ik, bkj, and there should be some over k. In case number of columns of A or number of rows of B are all equal to n. And when this repeated indices appear, we just remove and write it as it is. So repeated indices means there's an implicit summation over these repeated indices. That is called Einstein summation convention. Okay. Okay, let us continue to study matrix. Suppose that we have a vector A can be expressed in terms of as a linear combination of basis vectors, and if the A is a three-dimensional vector, three-dimensional Cartesian vector, then it can be expressed as a linear combination of x-axis basis, y-axis basis, and z-axis basis. Coefficients are called components, A2 and A3. And this one can be expressed as a summation over I, AI, EI. The unit vectors are normalized to be E1 dot E1 equals 0 and E2 dot E1 equals, this one is 1. So EI dot EJ equals delta IJ, Kronecker delta. If they are the same, it is 1. If they are different, indices are different, then it is 0. So the component AI can be obtained by taking the scalar product between EI and vector A. So if I substitute this one in here, A vector can be expressed as A scalar product with the EI, and this is a scalar, and multiplied by the unit vector, and summation over I is assumed. So if I have these three components as a Cartesian vector, then we have a matrix representation. That means this A is a column vector whose elements are just E1 component, E2 component, E3 components. So A1, A2, A3. This is another way of expressing a vector as a column vector. This is a column vector consisting of Cartesian coordinate. Kronecker delta, I already explained. Number 15, we have a Kronecker delta algebra. First A, delta ij, delta ij. This is, Kronecker delta is a symmetric, so I can write it ji, ij. This is a ji element of identity matrix, and this is ij element of identity matrix. So actually this is identity matrix ji element multiplied by identity matrix ij element. If these two indices I repeated, I can rewrite as a product of two matrices, and just copy this J and copy this J. I know that the product of identity is just identities of JJ. This one is actually matrix identity. It's a trace. Now, identity matrix is something like that. If it is an n by n identity matrix, then the trace is n. Okay. Next, delta ij delta jk. In a similar manner, I have identity multiplied by identity ij, identity jk, j are connected, so this is identity ik. Identity ik is just the Kronecker delta ik. Next one. Aij delta jk bkl. This is again A matrix ij element, identity matrix jk element, B matrix kl element. jj, kk are connected, so this is just A, 1, V, and I, and L. Identity matrix disappears if it is multiplied to something else, then it's just a product of A, B, I, L. Okay. Next. Delta ij, Aij. Because delta ij is 0 if I equals 0, so this product summed over I and j is, let us first write this one as identity symmetric, so ji, aij, so it is identity a, jj, a, jj, that is trace of A. We define a set of three-dimensional basis vectors E1, E2, and E3. We know that. So E1 dot E1 equals 1, E2, E2, 1, E3, E3 equals 1, E1 dot E2 equals 0, E1, E3 equals 0, E2, E3 equals 0. That are all expressed as EI dot EJ dot equals Kronecker delta. And we know the cross product E1 cross E2 equals E3, and cross product is anti-symmetric. So E2 cross E1 equals minus E3. E2 cross E3 equals E1. E3 cross E2 equals minus E1. And E3, E1, E2, E1, E3, minus E2. All these expressions are compactly expressed as EI cross EJ equals EK, here, IJK. And this is called the Levi-Civita tensor. By making use of this, we define scalar product of A with the cross product of B and C. This one is triple scalar product. This triple scalar product I have B, C, they are on a plane. The magnitude of B cross C is the area of a parallelogram spanned by B and C. And direction of this B cross C is perpendicular to that plane. If I introduce a vector A, it does not have to be perpendicular to the plane. In general, it should be something like that. And there should be some angle between A and B cross C. If theta equals half a pi, then the volume generated by these three vectors, actually that is the parallelepiped, something like that. This theta gives magnitude of A multiplied by magnitude of B cross C multiplied by cosine theta. And here, A cosine theta is actually the height of the parallelepiped. That height is measured perpendicularly from the plane spanned by B and C. So, geometrically, the triple scalar product is the volume spanned by these three vectors. That volume is just parallelepiped. We further study the Levi-Civita tensor. Levi-Civita tensor is defined by this triple scalar product of the three unit vectors of the Cartesian coordinate system. EI dot EJ plus EK. Sure, one must not compute this scalar product, but we have to make this operation, this cross product first, and then take the operation for the scalar product. And this value is defined by epsilon ijk in the three-dimensional space. For example, E1, E2, E3 equals E2 cross E3 equals E1. Therefore, the whole result is E1 dot E1. That is identity 1. Suppose that we have this is epsilon 1, 2, 3 is identity. What happens if I replace this order? Then I would get this is a minus E1 hat. So if I take the scalar product with the E1 hat, I have negative sign except for this magnitude is the same. We notice that epsilon 1, 2, 3 is at 1. But if I exchange the two numbers, two indices, like this, then I would get the negative sign on it. The values are the ijk's are called permutations if they are all different. We have three numbers available, 1, 2, and 3. So we have 3 factorial as a distinct permutations. That is 3 times 2 times 1. We find that it is 3 plus 2. There is a factor of 2, so 3 times 3 plus 2, 3. We say there are 3 even permutations. And we have another odd permutations. We say if epsilon ijk equals 1, then they are even. If epsilon ijk is minus 1, then we would say it's odd permutation. If I put 1, 2, 3 arbitrarily to these ijk's, then we have all possible cases, 3 times 3 times 3. There's 27 cases. Among 27 cases, all 3 cases plus 1, 3 cases minus 1. This is an even permutation and odd permutation. And 21 cases, 0. Even permutations are summarized as in a cyclic order, 1, 2, 3. If I exchange these two, this is even, and I would obtain 1, 3, 2. This is odd case. If I exchange these two, then I would get 3, 1, 2. That is even. You can check the triple scalar product. And then we replace this order. Then from even, I have odd permutation. 3, 2, 1. And then replace the first 2 elements to indices. Then I would get even permutation. 2, 3, 1. Finally, I can exchange these two numbers to obtain 3, 1, 2 as the last entry of the odd permutation. These 3 cases are even permutations, and these 3 cases are odd permutations, and then remaining 21 elements are all 0. There are some special cases. I have epsilon ijk squared. That means ijk, epsilon ijk, epsilon ijk. Here, I is repeated, j is repeated, and k is repeated. All 3 indices are repeated. We remember non-vanishing elements of epsilon ijk, there are 3 factorial cases. And among 3 factorial, we have the 3 plus 1 elements and the 3 minus 1 elements. They are even and they are odd. Because they are square, I have the 3 elements plus 1 squared, and I have minus 1 element squared multiplied by 3, because 3 permutation for odd and 3 permutation for even. Therefore, the answer is 6. This 6 is just 3 factorial, this number of permutation. In a similar manner, I can consider the Levi-Civita tensor for rank 2 case, epsilon ij. Then I have 2 elements, so I and j are 1 or 2. There are 2 times 2, 4 possibility of having arbitrary indices, but if I want to choose a permutation, these two indices must be different. In that case, I have permutation 2 times 1, 2 factorial as a permutation. So if this was the problem, then this result is one single permutation. I have epsilon 1, 2 as a plus 1 as an even permutation, epsilon 2, 1 as an odd permutation minus 1. So 1 times plus 1 square, single case, minus 1 square, this 2. 2 factorial is the number of permutation. In a similar manner, if I have I, j, k, l, 4 indices, square, the answer is 4 factorial. If I have I1 to In, square, the number of permutation for n different numbers will be n factorial. Okay, that's it for today. Let us continue to study Levi-Civita tensor. We have epsilon I j k epsilon I l m. This one can be written as epsilon I is summed over, so epsilon 1 jk epsilon 1 lm plus epsilon 2 jk epsilon 2 lm plus epsilon 3 jk epsilon 3 lm. Okay. First, epsilon 1 jk epsilon 1 lm equals either plus 1 or minus 1. If it is plus 1 or minus 1. If it is plus 1, then we have these two factors of plus 1 and plus 1, or minus 1, minus 1. If it is minus, these two factors are plus 1, minus 1, or minus 1, plus 1. Okay, this is minus minus. Let us consider plus plus first. Plus plus, that means epsilon 1, 2, 3. And this is epsilon 1, 2, 3. And minus 1 is minus 1 is epsilon 1, 3, 2, epsilon 1, 3, 2. This is minus minus case. And plus minus epsilon 1, 2, 3, and minus epsilon 1, 3, 2. This is the case. And minus 1 plus 1 epsilon 1, 3, 2, epsilon 1, 2, 3. This is the case. If I look at JKLM, this case, this 2 and these 2 are the same. So J and L must be the same. And this one, K and L must be the same. Here, 3, 3. J and K must be the same. K and L must be the same. Okay, so this is the case. if J and L are the same, JL, K and L are the same, we have plus sign. And this negative sign, J and M are the same, and K and L are the same. Then we have negative sign. In summary, this is the case for JK is 2, 3. JK is 2, 3. And in this case, JK equals 3, 1. And this case is JK equals 1 and 2. If I list all these cases, the final result is delta JL delta KM minus delta JM delta KL. This is the answer. We can further track this complicated formula. Epsilon ijk square is 3 factorial. Okay? What happens if I have epsilon ij a epsilon ij b? In this case, I, j, they are always the same. So, for example, 1, 2, then this one should be 3, something like that. So, the final answer should be, the answer should be non-zero only if A and B are the same. But I don't know what the coefficient is. However, if I multiply delta AB both sides, the left-hand side becomes ijk squared, because delta AB is this. If I multiply delta AB, then this is just epsilon ijk squared, and then this one is just trace of identity in 3 dimensions. I have 3c. Am I right? Yes, 3c. And I have constraint 3 factorial. From this, we obtain that c is 2. That means epsilon ijk, epsilon ija, epsilon ijb equals 2 times delta ab. Let us check this formula of the normalization. So I have epsilon ija, epsilon ijb equals 2 times delta ab. We have just found. But I have epsilon ijk ilm. Suppose that we do not know the overall normalization. Let me call this one as D delta JL delta KM minus the delta JM delta KL. If I multiply these two, delta JL, so delta JL to these both sides, then I would obtain the similar form as the left-hand side of first one. If I multiply this, I would find the epsilon ijk, epsilon ijm. And right side becomes JL is multiplied here. Delta JL, 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 JL. That is just 3. Delta KM, and this is JL, JL. This is connected, so delta minus delta KM. That is 2D delta KM. From this one should be 2 times delta AB. AB is replaced by KM, so delta KM. Therefore, I would obtain D equals 1. Thus, our formula has the correct normalization. Next, we consider the determinant. We remember the triple scalar product, just considered previously. Let us consider determinant of this 3 by 3 matrix. For simplicity, we consider the case the first row is a Cartesian vector A. The second row of this matrix is Cartesian vector B, and third row is the Cartesian vector C. Then the determinant of this 3 by 3 matrix A is defined by just a triple scalar product of this A, B, and C. And this triple scalar product of A and A, B, C is, remember, A now I wrote row vector just the determinant is just the triple scalar product of these 3 vectors. For example, A dot B cross C equals AI BJ CK epsilon IJK. Am I right? So substitute this A. This one is just A1, A2, A3, and B1, B2, B3, and this one is a C1, C2, and C3. So IJK AI is A1I, right? BJ equals A2J. CK is A3K. And as we remember, these numbers are either plus or minus. Plus elements are, there are 3 plus elements and there are 3 minus elements. And for IJK, if it is a 1, 2, 3, 2, 3, 1, 3, 1, 2, they are all, their Levi-Civita tensor are all plus 1. And 1, 3, 2, 2, 1, 3, and 3, 2, 1. They are all minus 1. So if I substitute all exact values, A1, A2, A3, 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 A1, A2, A3. This is just the determinant of this 3 by 3 matrix. Okay, next one. If we exchange the first two rows, then we find that the over negative sign. That is, you remember, epsilon ijk is equal to epsilon jik, put a negative sign on it. Because if I exchange it any two numbers in the Levi-Civita tensor indices, then I would get negative sign on it. That means this ijk means this is a row, this is the first row, second row, and third row. ij exchange is just exchange of columns. So in this case, the two rows, if I exchange two rows, then we find that if I exchange two rows, by definition of the triple scalar product, if I exchange two rows, I exchange B and A, for example, B and C, or C and A. Exchange two vectors, then the triple scalar product becomes has the flipped sign. If we exchange the first two columns, then we find that negative sign on it. That is directly coming from the Levi-Civita tensor. ijk here stands for the columns, column in the indices. So if I exchange it, then the over sign becomes negative. In a similar manner, although we have original definition for determinant of 3 by 3 matrix, epsilon ijk, a1i, a2j, a3k, I can write it as, for example, a2i, a1j, a3k, ijk with negative sign. And these can be made in a similar manner. All these values are the same. So if I exchange these row indices, all those values will be the same up to the over coefficient, that is either +1 or -1. +1 for even permutation. 1, 2, 3 is even permutation. 2, 1, 3 is odd permutation. For even permutation, it is +1. Odd permutation, -1. So, I can write it. PQR, epsilon ijk, AP, AQJ, ARK, and sum over PQR. Then we have a multiplicity of 3 factorials. So if I divide these value by 3 factorial, this is again the determinant of A. Next, we consider some applications of determinants. First, determinant of A. Sometimes we write it in this way, or determinant of A, something like that. determinant of a transpose matrix is also or the same as the original determinant of the original matrix, and that can be easily verified by the formula. For example, we have just seen that this relation can also be used to verify the determinant of the transpose matrix is identical to the original matrix. Okay, this one we already have verified by introducing the definition in terms of the triple scalar product. This formula can also be used to verify the identity or determinant AB. Here, we skip the verification. You can just follow the calculation to verify them. If I have a product of two matrices, the resultant matrix has the determinant, which is the product of two determinants. This one is very useful to find the determinant of inverse. Here, if it is invertible, that means that there exists an inverse matrix, then the product should be identity matrix. And as you can see, identity matrix has a determinant that is exactly 1. Because a non-vanishing element for all permutations, there's a single permutation, 1, 2, 3, 4, so something like that. So this is identically 1. Therefore, inverse determinant of the inverse matrix is reciprocal of the original matrix determinant. Okay, that's it. Okay, let's continue to consider the determinant. And actually, the determinant can be used to calculate the cross product of two three-dimensional vectors. In mathematics, a matrix is defined in a field, so all of the elements are in the same set. But in physics, we have some freedom. Here, the first row consists of 3 unit vectors. They are vectors. The second row and third rows are for the components of 2 three-dimensional vectors A and B. A vector A can be expressed as a linear combination of 3 unit vectors, Cartesian unit vectors. So A1, E1 plus A2, E2 plus A3, E3. Vector B can be decomposed into 3 unit vectors in a similar manner. Then we'll find that the first A vector is just the sum of AI, EI. And vector B is also a sum of components multiplied by unit vectors. It's a BJ, EJ. These coefficients AI and BJ are real numbers and they commute. So I can factor these out as AI, BJ. And then we end up with the cross product of EI and EJ. As we know, this cross product of 2 Cartesian unit vectors is just epsilon ijk ek. Alright, and then we end up with the expression AI, bj, ek multiplied by epsilon ijk. this EK can be shifted to the left. For example, EK, AI, BJ. Then epsilon ijk can be replaced with by exchanging J and K first, then I have negative sign on it. And I can make another exchange of I and K, then I would get negative sign, one more negative sign to make the plus sign for epsilon Kij. If I bring this one in here, I would get epsilon Kij, Ek, Ai, Bj. Now, I, J, K are all dummy variables. I can always replace them with the different values, just dummy variable. So K is replaced with I together. KK is replaced with II. II is replaced with JJ. And JJ is replaced with KK. Now we go back to the definition of determinant of three vectors. These three, the Cartesian components of elements. So this is the first row of that matrix, and this A1, A2, A3 is the second row of that matrix, and this is the third row of that matrix. Therefore, this A equals B is actually can be expressed in terms of a determinant of matrix that is composed of three unit vectors and two components of the two vectors. We have very important formula that is called the back cap rule. Back cap rule. Perhaps I have some calculation somewhere around here. Next page, perhaps. Here it is. Let me show you the proof of back cap rule. I want to compute A times, open the parentheses, B times C, close the parentheses. The first vector, A vector, we can treat this one as a single vector product of A vector and B cross C vector. Then this is just epsilon ijk, where I is multiplied to the unit vector ei, and this j matches to the vector index of the first vector, and k matches to the vector index for B cross C vector. Then the kth element of B cross C vector can be computed as this one. Remember, epsilon ijk is in here, eiaj is copied in here. B cross C's kth component is epsilon kpq, where p and q are the vector indices for B and C. Now we notice two factors for Leibniz-Vita tensor. Bring this epsilon ijk here, bring this epsilon kpq here, and then just copy eiaj right here and copy this bp and cq in here. We remember this epsilon ijk can be replaced with epsilon kij because k, in order to bring this k to the left-hand side, you have two exchanges with j and I. Thus, I have negative sign, double negative sign to have positive sign. So epsilon kij, epsilon kpq appears. And if one index is repeated, we had a formula. That formula is delta IP and delta JQ. That is a positive sign. When they are exchanged, delta IQ and JP, then it has negative sign on it. And then we copy EI hat, AJ, BP, CQ in here. Now, let us multiply this first vector to the right side. Delta IP, once delta IP is multiplied in here, I can replace P with I. I find that just copy EI, AJ in here, and then with the delta IP, I can replace the index P with I. So BP is now replaced with BI. And then delta JQ replaces the index Q with the index J. So we end up with CJ as the first term. The second term can be calculated in a similar manner. I have negative sign on it. EI is copied, AJ is copied, and IQ replaces the index Q with the I. This one has an index Q, so CQ is replaced with the CI. Then delta JP replaces the index P with the index J. So I have BJ. Okay, then I can find repeated indices AJ, CJ, and AJ, BJ in each term. In the first case, I factor these AJ, CJ out to have EI, BI, AJ, CJ. Subtracted by EI, CI, AJ, BJ. Now, AJ, BJ can be expressed in terms of the scalar product of vector A and vector C. EI, BI, sum over I is just a vector B itself. In a similar manner, AJ, BJ is a scalar product of A and B. EI, CI is just a vector C. This is the proof of back cap rule for the triple vector product. This A cross B cross C is back cap, proportional to term composed of term proportional to B and term proportional to C. Do you know why term proportional to A is missing? Yes, it is very simple. Because A cross means this resultant vector is perpendicular to A, so it does not have a component at all. Next, we can consider the determinant for n by n square matrix. We recall that if I have two by two matrix, for example, determinant A equals epsilon ij a1i a1j. This one can also be expressed in terms of 1 over 2 factorial epsilon pq epsilon ij ap I aqj. This is 2 by 2 case. 3 by 3, that was the starting point of our study of determinant. 3 by 3 in a similar manner, epsilon ijk a1i a2j a3k. And this one is again 1 over 3 factorial p q r I j k a p q r I j k. In a similar manner, extension to n by n matrix is also possible. Determinant of A for n by n matrix is epsilon I1, I2, and In. And I have 1i, 1, A2, I2, an, In. In a similar manner, I can factor out 1 over n factorial epsilon j1, jn, epsilon I1, In, j1, I1, a, j2, I2, jn, In. This is the most general form of the definition of the determinant of A. And in this determinant, we have Levi-Civita tensor that is the generalization of n permutation cases. That is a simple generalization, so I don't have to explain in detail. That's it.